We better start, I'm late already. Speaking of government grants and annoyances related to them, let's talk about power calculations. This is another area that doesn't really get covered in introductory statistics courses, mainly because doing these calculations by hand is a total nightmare, and they didn't want to torture introductory students with it. But I think it's worth teaching now because, number one, it's easy to do in R, and number two, any grant application you write is going to require this, and number three, this is, for most statisticians, far and away the number one thing that you get asked for help with, that somebody's writing a grant and needs some power calculations for it. So I figured it's worth giving the basics on how to do that. And I guess before I dive too far into this, I should announce, if you didn't see the email, I had forgotten until this morning that our usual room for the discussion section is booked this morning, so we had to move it to another room. It's 3615 in Curry. Every other week it'll be back to the normal room, G5112 or whatever it is. Also, homework 3 is due midnight tonight. There's the usual 1 week grace period, but you'll get the bonus for turning it on time if it's turned in today. But anyway, power. So, quick review of the general hypothesis testing framework. When you perform a hypothesis test, you define a null hypothesis H0 and alternative hypothesis HA. Type 1 error means that you reject the null hypothesis when it's true, and type 2 error means you fail to reject the null hypothesis when it's false. Hopefully everybody remembers this much. And power of the statistical test is defined to be the probability of rejecting your null hypothesis given that your null hypothesis is false. In other words, you're testing a drug or something like that, you're trying to see if the drug is more effective than the placebo. The power of your test is the probability of rejecting the null hypothesis of no difference, given that there really is a difference. The drug really is more effective than the placebo. So higher in power implies that you have a better probability of detecting a truly significant result. And if you don't have a large enough sample size, your test won't have enough power, which raises the question you don't want to waste money collecting more samples than you need, but on the other hand, you want to make sure that you have enough samples to be able to reject your null hypothesis, assuming that it's false. And government funding agencies are aware of this, so generally speaking, before they'll fund your study, they'll ask you to do some power calculations to show that your proposed sample size will give you enough power to be able to find the result that you're looking for. So, first, I'll just consider a couple simple scenarios for power calculations today. The first scenario is you're going to test hypotheses about the sample mean. That, say you want to test the null hypothesis that the mean of a population equals a certain value, or that two populations have equal means. Say you give a new painkiller and a placebo to two groups. You want to test the null hypothesis that the mean pain levels, or the mean differences in pain, or the difference is different between the two groups. So what factors will determine the power of this type of study? So, the first thing that your power will depend on is your significance level alpha. That, as you'll recall, when we perform hypothesis testing, typically you'll reject the null hypothesis if p is less than some cutoff alpha. In practice, alpha is pretty much always 0.05. And by doing this, you choose a certain level of protection against type 1 error, assuming that the assumptions of whatever test you're using are satisfied. Then the probability of type 1 error under this framework is alpha. So if you reject your null hypothesis, if your p-value is less than alpha, then there should be about a 5% chance of rejecting your null hypothesis if the null hypothesis is true. And in general, by protecting against type 1 error, you increase your risk of type 2 error. So, for example, if you demanded a more stringent threshold of p less than 0.01, then you're less likely to reject your null hypothesis, which means that you increase the likelihood of failing to reject your null hypothesis, given that it's false, and therefore your power goes down. Well, I say in practice, usually everybody uses 0.05, so you don't worry about this criteria too much. Another thing that affects the power of your experiment is the standard deviation of the data that we denote by sigma. As you'll recall, the standard deviation of the sample mean is sigma divided by the square root of n. That implies that the bigger sigma is, the more variability there will be in the sample mean, so that a given sample produces less reliable information about the population mean. So in other words, if you try to test the null hypothesis that the mean is equal to a certain value or equal to the mean of another sample, higher sigma implies you're less certain about the true value of the mean, and implies you have lower power. So as much as you can, you want to try to make your sigma, your standard deviation, as small as possible when you design experiments. Now, in practice, usually you have relatively little control over this, but if you can do something to reduce it, it's good to reduce it. And likewise, the power of your test will be related to the sample size n, that a standard deviation of the sample mean, as I said, is sigma over the square root of n, so that implies that as n increases, the standard deviation of the sample mean will go down. The higher your n is, the more information you have about the sample mean, the better your power to test the null hypothesis that the sample mean is equal to a certain value. And I mean, larger n also gives you more information about sigma, which will also give you better power because it will increase the number of degrees of freedom in your test, although in practice, once you get to about 30 or 40, it doesn't help you that much because your t-distribution is essentially a normal distribution anyway at that point. And the other thing that your power depends on is the true difference in means, mu1 minus mu2, that is the difference between the mean of your population of interest and your hypothesized mean, or the true difference in means between the two groups that you're comparing. So other things being equal, it's easier to detect a large difference than a small one, not surprisingly. So if the difference between the hypothesized mean and the true mean is large, you get better power. Easy enough, hopefully. So, how do you calculate the power? As I noted at the beginning of class, you have to use some weird statistical formulas that are really complicated, and historically they didn't teach this in introductory statistics classes because these formulas were so painful. Nowadays, luckily, we have R. Calculating power is relatively easy, so I'm going to show you how to do it so that at least simple power calculations in grant writing you'll know how to do yourself. So, let's take like a simple example that I found in a textbook somewhere that say like the average height of 17-year-old males is 69.1 inches and the average height of 17-year-old females is 64.1 inches, and standard deviation in both groups is about 2.5. So let's say that we measure the heights of 11 17-year-old males, 11 17-year-old females, and we want to test the null hypothesis that the mean height of the two groups is equal. How much power do we have to detect this, to test this particular null hypothesis? Well, the command that you use in R is power.t.test, and this is kind of an unusual command in R that it takes 5 possible parameters, and you have to specify 4 of them, and whichever one you do, and the 5th one that you don't specify, it gives you. So in this case, I give it the 4 possible parameters. So first of all, the sample size n. Second is delta, which is the true difference in the means. Third is the standard deviation. In this case, it's assumed to be the same in both groups. The fourth is the significance level. Like I say, in practice, you'll almost always use 0.05, and I believe that's the default in R. The fifth parameter that I don't specify here is the power. So in this case, I say, based on a sample size 11, note that it's 11 in each group, not 11 total. True mean difference of 5, standard deviation of 2.5, perform the test at 0.05 level. What power do I have for rejecting the null hypothesis of no mean difference in these two groups? And I get a power of about 0.99, indicating with a sample of size 11, if I do 2 sample t-tests of 11 17-year-old males, 11 17-year-old females, I'm almost certain to detect the difference.
Sorry, what does power mean in this context?
Power is the probability of rejecting your null hypothesis given that your null hypothesis is true. So this is saying, assuming that the true mean difference is 5 inches, if I take 11 males and 11 females, do the t-test comparing the two, what's the probability that I reject the null hypothesis that the means are equal? So in this case, unless you get an extraordinarily unlucky sample, you would end up rejecting the null hypothesis if you perform that particular experiment. So, as I said, that you have to specify 4 of the 5 parameters: the sample size n, the difference between the means, the pooled standard deviation, the significance level, and the desired power level. In practice, it will usually be either the sample size n or the power that you don't specify. Either you'll say, I have a sample of size 11 in each group, what power what power will I have if I perform this test? Or you'll say, what sample size do I need in order to get a power of 0.8 or whatever? So, as I just said, let's say that we want to change this slightly. Let's say that instead of calculating the power for a sample size 11, let's say that I'm going to design this experiment and I want to know how many subjects I need to obtain 80% power for testing the null hypothesis of no difference between the two groups. In this case, I'll do power.t.test and I'll specify the power rather than the sample size. So here I say power.t.test, delta, standard deviation, significance level, or as before, and then I say power equals 0.8, and then it calculates the sample size that I need in each group in order to get 80% power. And you'll note that when power.t.test does this, it will give you a sample size that's not an integer generally, which, I don't know, to me is a little bit silly, but such is life. In this case, in general, for the purpose of this class, if it gives you something that has a decimal part, just round to the next whole number, because you can't get a sample of size 5.09, obviously. If you get a sample of size 6, you have enough power. I mean, in this case, given that it's just barely over 5, maybe you could say, I'll take a sample of size 5 and have power just barely below 0.8, but yeah, like I say, for the homework, I would just say 6, and we'll give you credit. And you can also you can also calculate a power for one-sided t-tests using power.t.test. Let's say that rather than doing the two-sided test, we do a one-sided test of the alternative hypothesis that males are taller than females against the null hypothesis that the means of the two groups are equal. In that case, you just have to tell R that you want to, that should say that you want to perform a one-sided test one of these days after about 10 years. Maybe I'll get rid of all the typos in these slides. Hopefully I remember to fix that tonight. So, and to do this in R, you would say power.t.test, all the same parameters, give it the sample size, the mean difference, the standard deviation, the significance level. Then you add this additional parameter, say alternative equals 1.sided. Now we have 99.8% power rather than 99.3% power. So, I mean, given that we had almost 100% power with the two-sided test, we don't get that much additional power with the one-sided test, but if your power was lower, you may be able to increase it substantially using the one-sided test. And this is always kind of a little bit dicey. I mean, in my opinion, in this particular case, using the one-sided test is perfectly reasonable, but a lot of journals will get suspicious if you use it. In fact, some journals actually require that you use only two-sided tests. I guess they're suspicious of people reporting one-sided tests because they think that you ran your test without expecting it, without necessarily having an alternative that it's less or greater. You got a p-value that just barely missed the cutoff, so you switch to one side to try to make the cutoff. And to be fair, people do that sometimes. But yeah, anyway. So in general, when you're writing power calculations, I would base it on two-sided tests, just so that you don't have a reviewer getting angry at you for doing the one-sided version. And let's say that rather than doing a paired t-test, you want to do a one-sample t-test that you just sample 11, 17-year-old males, and you want to test the null hypothesis that the mean height is 65 against the alternative that it's something other than 65. In this case, you're doing a one-sample test, so you have to modify the R command accordingly. In this case, all the parameters are the same except that you add this additional parameter type equals 1.sample. That tells R that you want to do a one-sample t-test rather than two-sample t-test. In this case, we get almost 100% power yet again. So, and again, I mean, there's nothing wrong with this test in principle. It's not going to make reviewers nervous like the one-sided test is. It's just not that commonly used. In my experience, when I use t-tests, I'm almost always comparing the means between two groups. Testing the null hypothesis, the mean of one group is equal to a specific value tends to be much less common. And as I said, in general, the power.t.test command, you have to give it sorry. You have to specify 4 of the first 5 parameters: n, delta, SD, sig level, and power. In general, you will usually specify delta, SD, and sig level, and then one of either n or power. Either you'll tell it what n do you need to get a certain power, or what power will you get for a certain n. Type and alternative are 2 optional arguments that you can use to do one-sided hypothesis tests or one sample t-tests if you ever need to do so. And so that's how you do power to test. That's how you calculate a power for hypothesis test about mean. Let's say you want to do power for hypothesis test about proportions. In general, power of hypothesis test involving proportions will depend on the true proportions P1 and P2, in addition to the sample size and the significance level. And the R syntax is very similar to the R commands that you use to calculate power for tests on the sample mean or means. So, to give an example of when you might want to do hypothesis tests on proportions, let's say that 60% of people who take an experimental drug experience pain relief, compared to 40% who took a placebo. And let's say we recruit 300 patients, and 150 receive the drug, the other 150 take the placebo. And what power do we have to detect the difference between these two groups? The command in R to do this is called power.prop.test. In this case, you give it the sample size, 150 in this case. Recall once again the sample size is in each group. In general, to do these power calculations, you have to assume that the number of people in both groups are the same. In general, if you have like 500 cases and 100 controls, your power is actually almost the same as if you had 100 cases and 100 controls. So if that situation arises, the n should just be the smaller of whatever your two group sizes are. This also illustrates that why, if you have any say in the matter, it's a good idea to try to make the sample size of your case and your control groups the same or approximately the same. You'll get better power that way. So in this case, say power.prop.test, sample of size 150 in each group. The proportion of success expected in the first group is 0.4. The proportion of success expected in the second group is 0.6. Use the p less than 0.05 cutoff as usual. In this case, we see we have about 93.7% power to detect the difference between these two groups. Like I say, the syntax is very similar to what it is for power.t.test, that you have to specify 4 out of 5 of n, P1, P2, sig level, and power. Again, in practice, it's almost always either n or power that you'll leave unspecified, and if you want to do a one-sided test, you can do this alternative equals 1.sided if you want. And to give another example of when you might want to perform hypothesis tests on power of a hypothesis test involving proportions, this is a study that I was actually involved with a short time ago, and hopefully to make you less cynical about what I'm going to say at the end of the lecture is to illustrate that sometimes power calculations are not total BS. Yeah, only sometimes, but in this particular study, it was actually kind of funny. It was my mom who asked me for help with this study. She's in charge of purchasing instruments for a big HMO in Utah, and this actual issue came up, that the surgeons that work in her company use some type of instrument. I think it's like some type of scalpel for cutting bone or something like that. I actually don't know all the details. And she can buy either new instruments or reprocessed instruments. And the reprocessed ones are obviously cheaper, but but she's had doctors complain that the reprocessed ones don't work as well, even though the company that makes them insists that there's no detectable differences between them and the new experiments, but nobody seems to have any scientific evidence on this one way or the other. So they wanted to design a study to compare the new instruments to the reprocessed instruments. So the study design is, in this particular study, the doctors will be given both a new instrument and a reprocessed instrument. Obviously, they won't be told which is which, and they'll have to cut into the bone using both instruments on the same patient, because bone density and things like that can vary from patient to patient, so they want to make sure they're doing an apples-to-apples comparison. And then at the end of the experiment, the doctor has to rate both instruments as either satisfactory or unsatisfactory. They want to see if the reprocessed instruments are more likely to be declared unsatisfactory. So my mom would know, so if we do this, can you calculate how many patients are needed for this study? And well, so I had to ask a number of questions for this power calculation other to perform. I said, first of all, okay, how certain do you want to be about this? For government grants, 80% is most commonly used. I have no idea why. The government thinks that if only 20% of grants fail due to lack of power, that's acceptable or something. Maybe we should write to the NIH and tell them to make 95% the required power level and we'll avoid sequestration or something like that. But yeah, I shouldn't even joke about that, should I? Anyway. And next question is, what threshold do you want to use for statistical significance? In practice, it's almost always 0.05. And then, what difference in proportions do you want the study to be able to detect? If the reprocessed instruments are no more than 5% worse than the new ones, would that be considered okay? What if they're no more than 10% worse? The other question is like, well, what proportion of instruments are expected to be declared unacceptable? Because you'll see here in a second that the power calculations depend on that as well. So let's say that we want to have 80% power to detect a difference of 10% between new instruments and reprocessed instruments, and suppose that we think that the worst case scenario, 30% of the reprocessed instruments will be declared unacceptable. In that case, then P2, the proportion of reprocessed instruments, would be 0.3. P1, the proportion of new instruments declared unacceptable, would be 0.2. Or to have 80% power to detect, well, that's an embarrassing typo. It should be 0.05, not 0.5. Oops. Well, I'm going to have to go home and try to fix this slide. But if you were using a significance level of 0.5, you would need a sample size of like 86. Now, in practice, you're not going to want to use a cutoff of 0.5. The true power would probably be greater. This illustrates the danger of trying to add new slides to my lecture at 2 in the morning. So, yeah. But repeating the same embarrassing mistake on the next slide.
So if you were to use 0.05, then the n would be incredibly higher.
Yes. But luckily for the take-home message I'm trying to get here, this mistake doesn't make that much difference for the take-home message, although I still am going to go home and fix this just so that I don't look like an idiot when I teach this in future years. If you assume that only 15% of the reprocessed instruments will be declared unacceptable, so I do P1 equals 0.05, P2 equals 0.15, note that the sample size reduces significantly. The take-home message being that if the proportion of successes or failures that you expect to observe is smaller, then then you need a smaller sample size to get the same power. And in general, power varies depending on the choice of P1 and P2 and the desired difference between P1 and P2. And in general, the closer your P1 and P2 are to 0.5, the lower your power is going to be. And so if you can say that your P2 is at most some specified value P0, then you can say P2 equals whatever that worst case scenario is, P1 equals P2 minus whatever difference you want to detect, and that will give you the best possible power. That raised the question, what if you have no idea whatsoever what your P2 is, and you want to choose P1 and P2 such as to make sure that you have enough power regardless of what the true P1 and P2 turn out to be? Well, as I said, that would be a cool homework question, wouldn't it? So I'll let you struggle with that on the homework a little bit, and if you get too frustrated, then you're welcome to email me. But I've given you a big hint right here. That is, the closer P1 and P2 are to 0.5, the lower your power will be. So to make sure that you have the power for any possible value of P1 and P2, you should probably choose, if you want to detect a difference of 0.1, for instance, you set P1 and P2 as close as possible to 0.5 such that the difference between the two is 0.1, and that may have given away the homework problem, but, useful information to know. So, in my opinion, when you're doing power calculations about proportions, if you're willing to make certain assumptions like that, you can, in general, come up with some reasonably accurate power calculations that will work across that should work regardless of what your true P1 and P2 are. Now, let's say that we're doing power calculations about means. To do a power calculation on the means, you need to know, like, the true value of the mean or the true difference in the means and the standard deviation under your alternative hypothesis. How are you supposed to know that? You don't. I mean, sometimes you can make an educated guess, but honestly, a high percentage of the time you're just making numbers up and just hoping that this is somewhere close to the truth, which is why I believe that in practice most power calculations, at least power calculations about the power you need for means, are like highly suspect in the best case scenario, totally bogus in the worst case scenario. And maybe I shouldn't make you this cynical, but if you want to know the dirty little secret about most power calculations involving mean, the way this is taught in textbooks and the way we like to tell ourselves that we do this is you have some preliminary data giving you information about mu and sigma, or you make an educated guess based on whatever information you have, and then you do a power calculation to see how large of a sample you need to be fairly confident that your study will reject the null hypothesis. And what really happens is down at the bottom, that you're applying for a grant, you have a budget for your grant that will give you a sample of size n. So you make up some values of mu and sigma that will make it so that miraculously a sample of size n exactly what you need to prove your null hypothesis. And yes, it really is as bad as I made it sound in the previous slide. I'm writing a grant right now, I'm basically doing precisely this. Basically, I know that the study is underpowered, and I'm trying to twist myself into a pretzel, trying to come up with some convincing argument that the experiment will work anyway. So, from a grantsmanship perspective on this, the best way, if you have some preliminary data that you can point to and say that my mu and my sigma are something like this, then that's the best case scenario. Most of the time you won't. And one way that you can try to spin this when you're writing a grant is if you can try to come up with some argument about why your estimates of mu and sigma are conservative, that can get you a fair amount of mileage. The argument would be that, like, worst case scenario, my mu and sigma are like this, that gives us enough power. In practice, these assumptions are probably pessimistic, so on and so forth. Brief example of this is another study that I worked on recently where I had to perform a power calculation that we wanted to see if there was a relationship between blood pressure and the risk of developing pain after surgery, because we knew from past experience that low blood pressure is associated with increased sensitivity to pain. And we know that if our grant gets funded, we will have enough money to recruit 76 patients who had recently had a root canal. And so we'll measure the patient's blood pressure prior to the operation. The patient will be instructed to keep a pain diary for 5 days, and we keep track of how many days it takes for them to report no pain. And we want to see if patients with lower blood pressure have pain for a longer period. So in this case, we actually had a small amount of preliminary data that we found that patients with low blood pressure took about 1.4 days longer to recover, with a standard deviation of about 1.5 days. So I calculated if we recruit 38 patients with low blood pressure and 38 patients with higher blood pressure, this gives us about 98% power to reject this null hypothesis at the 0.05 level. And if the true difference were 1 day instead of 1.4 days, we'd still have 81.8% power to detect this difference. And there's another typo, but so I wrote in the grant application something like this, like, even if our estimate of the true mean difference were so horribly off that it turns out to be 50% smaller than what we saw in our preliminary data, we would still have 80% power to detect this association. And hopefully, we wouldn't really be off by 50%, so even if we make conservative assumptions, we can conclude that 76 patients will provide adequate power to this study. You can spin it something like that. I mean, just try to come up with some reason why the numbers that you plugged in are conservative so that you can say, even if these numbers are wrong, we still have enough power, sort of thing. And I mean, honestly, writing a power section for a grant, it's almost as much of a persuasive writing exercise as it is a statistical exercise. It's just a matter of selling it to a funding agency as much as it is plugging in numbers. If you need help with this, consult a statistical expert. We are extremely used to this. Being asked to write power sections for grants is probably the single thing that we get asked to do more often than anything else. So, things to remember today: power calculations. If you ever write grants, you're going to need to do this. You may need to do it for other reasons as well. The power will depend on the sample size, the significance level that you want, and the effect size, the true difference in means, or the true difference in proportions, or whatever. And in general, you won't know the effect size in advance, so you just have to improvise / guess, sort of thing. And the R commands to remember for this are power.t.test and power.prop.test. As I said, you typically have to specify 4 of these 5 parameters. Any questions about any of this or anything else?
So I didn't really understand the part of why a test would have more power if the difference is, say, from 0.15 to 0.5 than if it is from 0.35 than 0.25.
Okay, the question was why you get better power for detecting the difference between like point 1 to point 2 than you would from point 2 to point 3. And I'm trying to think of an intuitive answer to that. I mean, the mathematical answer just off the top of my head is, if you'll recall from several lectures back, you probably don't, but for large n, the standard error of an estimated proportion is equal to the square root of p times 1 minus p divided by n. So basically, p times 1 minus p will be maximized at p equals 1/2, and will get successively smaller as p moves away from 1/2. So the value of p that will give you the largest possible variance is precisely p equals 1/2. Now, is there an intuitive reason behind that? Well, I mean, I suppose the obvious example would be the extreme scenario that if, say, like P1 equals 0 and P1 equals 0.1, that means if P1 is 0, then you're never going to get a success for that particular group, no matter how large your sample size is. You get some successes for the other group. And the fact they're getting 0 successes in one group and a few in the other, that gives you very strong evidence to assume that there's a difference between the two groups. Or, I mean, I guess just like, say, you do like 100 trials, say like P1 equals 0.1, P2 equals 0.11, for instance. You get 1 success in the first group, 11 in the second group. You get 11 times more successes in the second group. You're like, okay, there's probably a big difference here. On the other hand, if you get like 60 in one group and 40 in the other group, that's like 1.2 times as many in the second group rather than 11 times as many, so you're not as confident that that's a real result, I guess. That's probably the intuition behind it. Any other questions? Okay. If you have issues with the homework, email me. Like I said, I really try my hardest not to torture people too much, and if the homework's driving you crazy, just send me an email, answer questions, or we set up a time to meet, or Skype, or phone, or whatever.